My name is Sven-Erik Gryning, and I will tell you about wind profiles, how they look in the atmosphere. What we should learn here is that when the lecture is finished, you should be able to understand the physics and the theory behind the wind profiles, so you have a deeper understanding of the wind profiles. And you should be able to understand why and know that there is a difference between the wind profile during the night and during the day. The wind profiles are more complicated than will be presented here, but this is a simplified version, you can say. So first we look at the theoretical background. The simplest form for the wind profile is a so-called logarithmic wind profile, and that is shown at the top here. The wind profile, the wind as a function of height, where z is height, is described as a function of the u star, which is the momentum flux. It's a function of height z, and it's a function of the surface roughness, and it's a function of the stability function. In neutral conditions, the stability function is 0. The psi there is the stability function. And therefore we have a purely logarithmic profile in neutral condition. Neutral condition means that there is no heat flux from the surface, so it corresponds to overcast conditions with high wind speeds. To the right you can see an example of the wind profiles. It's driven by a geostrophic wind, in this case 12 meters per second. And the geostrophic wind is a wind that drives the wind near the surface. It's the wind speed at about 1 kilometer's height. It's characteristic that the wind varies a lot near the surface during the day and the night. The black curve is the neutral wind profile, and in this representation here, where the y-axis is logarithmic, it can be seen as a straight line. During the night, it's difficult for the energy to come to the ground because of the reduced momentum flux, and the wind speed reduces near the ground. This is represented by the green line, but you can also see that although the wind speed is low near the ground, it increases fairly fast with the height, and at about a height of 100 meters it can sometimes even be faster than the neutral wind speed. During the day there is a better connection to the geostrophic wind. You have a higher wind speed during the day than during the night, and it is represented by the red curve. You can also see that the wind speed varies little with height during the day because of the big eddies and because of the efficient mixing during the day. So already here you can see that the wind speed during the night and the wind speed during the day are very different, close to the surface. But you can also have an idea that about 100 meters above, the conditions are quite different. So one of the parameters in the in the logarithmic wind profiles is surface roughness, Z0. And here we have an example of 4 classes of surface roughness. This represents sea conditions where the surface roughness is very, very low. In this case we have set it to 0.0002 meters, and this is a fairly characteristic value for sea. It's also characteristic that the roughness of the sea is not a constant, but it varies with the wind speed. If you look at a landscape like this, you can see that it's an open landscape with grassland, but you can also see that it's quite free, so the wind can easily blow over the landscape. We consider this to have a roughness about 3 centimeters. In this case down here, we have farmlands, we have more vegetation, and vegetation is very good to drag momentum out of the wind and reduce the wind. So we assign this to a roughness of about 0.1 meter. And in this case here you have many shelter belts, or you can have a forest, small forest. and we think that this has a roughness about 40 centimeters. However, it's characteristic that it's very difficult to estimate the roughness. You need very, very careful measurements, and therefore it's often better to use predetermined values. And here we have an example of the roughness length put up as a table. And as can be seen from the table, again we have at the bottom the roughness for the sea, very, very low. And we also have, for example, mown grass, the bare soil of the order of 1 centimeter. Shelter belts has again 40 centimeters. But we have recently come to the conclusion that the forest can have a quite high roughness. There's still some discussion about the roughness length of the forest. In this case, we have set it to 80 centimeters, and it's also characteristic for the forest that a dense forest has a lower roughness than a sparse forest, and a sparse forest can be up to 1.5 meters in roughness. So it's often better, if you don't have really high quality measurements of the wind profile, to use the Z0 determined from a table like this. So this is an example how the wind changes during the day and as a function of height. Here we have land conditions, and you can see that in this case 30 meters we have, as we explained before, low wind speeds during the night. It increases during the day because you have the convection that starts, you have the efficient mixing of the energy from above, and then during the night it decreases again. These are real measurements. If we go a little higher at about 50 meters, we have the same variation, but the difference between day and night is lower. And at about 150 meters in this case, which is a rural case, we can see that there's very little variation between the wind speed during night and during the day. And then it's quite interesting that above that we have higher wind speeds during the night than during the day, and the effect is very strong. And we will come back to this effect in a moment. This is land conditions. Water conditions, it's different because over water you don't have the heating of the water and the cooling of the water during the night and the heating during the day. And therefore you can see that the structure of the wind speed as function of height does not have the characteristic pattern as it has over land. So this is the atmospheric stability that controls a lot of this. And here we have an example of the daytime mixed layer. It's characteristic that when the sun is shining, you heat up the ground, and because you heat up the ground, you create motions in the air. The air becomes lighter than the surrounding air, and eddies start. Here, near the surface, we see that the eddies are very small. Basically, they scale with the height of the above ground, and they transport heat from the surface and up. But during the day, this transport gets higher and higher, and at a certain time you have the formation of very large eddies. And on the top of this you have the so-called entrainment zone. This is a zone where free air is entrained into the boundary layer. The entrainment zone can have various thickness, from 10% of the boundary layer height to maybe 20% or even more in the morning. So it's characteristic that the convective boundary layer has very, very large profile, very, very efficient mixing, and therefore the wind profile, because of the efficient mixing, becomes near constant with height. When you get to the entrainment zone, it starts to increase or have a characteristic pattern. This arrow shows that the air is trained into the boundary layer. During the night it's different. Here we have a similar schematic picture of the night conditions, but the height is much less. It's only 300 meters. And it has in a way 3 layers, you can say. First we look at the temperature profile. It increases because the surface is cooling, and then it has an area where it's near constant, and then it has an inversion and then it's in the free atmosphere. So in the blue part, which is very low, close to the surface, you can see that we have eddies and they are continuous, but they are not very efficient because momentum flux is inhibited from above. It's difficult for the eddies to form. It's mainly mechanical turbulence and some gravity waves, which is illustrated by the long arrows here. Then you have this layer with continuous turbulence. Above this you have a layer where the turbulence is not continuous, but it still exists and it can come in bursts and such things. And on the top of this layer you have you can see you have an inversion or a kind of kink. So this is you have a layer with full turbulence, you have a layer with intermittent turbulence, and then you have the free atmosphere above. So what does the wind profile look here? Yeah, it's completely different from the daytime, because the wind is very small near the surface, then it increases, and it increases very fast in the stable boundary layer, and it actually here on this can form a low level jet, and then it starts to decrease because we have a low level jet here. And this is partly the explanation that when you get up to about a height of 100 meters, or the wind speed during night and day are near equal, because you have the formation of low level jets. So here are some examples from the wheel of the wind profiles during day. We have low wind on a sunny day, and here we see that the wind speed is low and near constant with height. The wind shear, the directional shear is also low because of the efficient mixing. If it's overcast, you have closer to neutral, you still have a low wind, a low directional shear, and but you have a more pronounced profile. This is completely different during the night. First of all, the wind speed increases much more during the night than during the day. It's near linear. The directional change is much bigger than during the day. And this is a windy night with a low level jet. You can see the formation of the jet, in this case about 300 meters, and a very pronounced directional shear. So in summary, what you should have learned in this lecture is that the wind profile is logarithmic at high wind speeds, but there are some. But the wind speed depends on the surface roughness, and winds are different during day and night. But I should say that the wind speed profile is more complicated than this, because this is in a way the simplified version. It also depends on the height of the boundary layer, as we saw on the slides, and it also depends on the horizontal temperature gradients in the atmosphere. So large scales effect actually starts to influence the wind speed already at let's say 100 to 200 meters.